Jai Hind everyone. This is Dr. Naresh Kumar from Akgec College, Ghaziabad. Welcome to the class of Optical Communication. In this video lecture, we will cover the topic Coherent Detection with its type, the Homodyne Detection and the Heterodyne Detection. So the main contents for this lecture will be, we will study the concept of coherent detection. Basically, we will study the concept of coherent detection in comparison with the direct detection. Then we will study what are the advantages of coherent detection, or we will study what are the advantages of coherent detection as compared to the direct detection. Then finally, we will study the two types of coherent detection schemes, homodyne detection and heterodyne detection, along with their advantages and limitations. So first of all, what is coherent detection? Basically, in the optical communication system, at the receiver side, the first component that we are using on the receiver side is photodiode or photodetector. This photodiode or photodetector basically converts the received or incidented optical power into the corresponding electrical signal. So basically, this photodiode converts the optical to electrical conversion. So O to E conversion is done by the photodiode along with the detection of the signal. That is, signal is converted into its original form, or demodulation is also performed at the detector. So this process is called as the detection. So detection is basically receiving of the optical signal from the fiber and converting it into the corresponding electrical form and into the original message signal with the help of a photodiode or photodetector. Now this detection is generally that we use in the optical communication system can be of two types. One is direct detection and another is coherent detection. As clear from the name, direct detection. Direct detection means the received optical signal is directly incidented over this photodiode or photodetector without any change. That means the diagram that I have shown here, drawn here, is this is the direct detection. That is, this received optical power from the fiber is directly incidented over the photodiode without any change. That means light directly incidented. Directly incidented without any change. In this process, we have certain limitations, like in the direct detection, the sensitivity is less. Sensitivity is less. The system is less sensitive. Another disadvantage that we get is here we can use only the ASK or OOK modulation scheme. Another limitation that we get over here is this direct detection or ASK can be applied only when the data rate is less than 10 Gbps. So these are the certain limitations. There are more limitations, like the tolerance towards the polarization mode dispersion as well as chromatic dispersion is less, and moreover the spectral efficiency of the system is also less. Spectral efficiency is also less. So to overcome these limitations, we are using the or proposing this coherent detection. So in the coherent detection, what happens? In the coherent detection, one, we have the source signal that was being transmitted, and then we use a local oscillator, local source, local oscillator, or we can say that local optical source. Another signal is generated from this local oscillator source, that is WL, and we ensure the power of this local oscillator is much greater than this received signal. So one we have is received signal from the fiber, another we have is another optical signal generated from a local source. Then the light of these two is coupled, or we can say that coupled or mixed, and then this coupled or mixed light is incidented over this photodiode or photodetector, and at this point, along with the magnitude, we also consider the frequency and phase. So all the limitations of this direct detection scheme can be overcome by this coherent detection. So in the coherent detection, what happens? We have a received signal from the fiber, then we have a locally generated optical signal from a local source, then these two signals are coupled together or mixed together and are incidented over the photodiode or photodetector. Then what we get here is the immediate frequency WIF, that is WS minus WL. Okay, so we get an intermediate frequency signal. So as we are using a local oscillator signal additionally, and the power of this local oscillator signal is much greater than the power of the received signal or source signal. So here the power incidented over the photodiode is comparatively more as compared to the direct detection. So what happens in this case? The sensitivity becomes better. Sensitivity gets improved, and all these advantages, all these disadvantages which were there in the direct detection becomes advantages or can be overcome with the help of this coherent detection. So in the coherent detection we get advantages such as sensitivity is better, along with ASK. In this case we are considering the frequency phase also, so we can also use ASK, FSK and PSK modulation schemes. Moreover, the direct detection can be used up to 10 Gbps, whereas this coherent detection can be used with data rate up to or more than 100 Gbps. And the tolerance limits in case of polarization mode dispersion and chromatic dispersion are comparatively better in the case of this coherent detection, and moreover the spectral efficiency is also better in the case of this coherent detection. So these are the difference between the direct detection and the coherent detection, and what are the limitations of direct detection that we can overcome with the help of coherent detection. So in summary, we can say that the received optical signal is directly incidented over the photodiode without any change is direct detection, or we can say simply the principle is known as the IMDD, intensity modulation and direct detection. Whereas in case of coherent detection, the received signal is combined with the locally generated another optical signal of high power, and then the combined signal is incidented over the photodiode or photodetector. So this is the coherent detection, and the signal incidented is here with intermediate frequency, and all the limitations becomes the advantage, like high spectral efficiency and more sensitivity. It can also be used with ASK, FSK and PSK, can be used with higher data rates, spectral efficiency is more, sensitivity is high. So all these are the advantages. So what is the need of coherent light wave system? That we have already studied. Earlier we have only the IMDD, which have certain limitations. To overcome these limitations or to have the advantages as discussed, like high sensitivity, better spectral efficiency, better tolerance for the chromatic dispersion and polarization mode dispersion, can also be used for high data rate, can be used for ASK, FSK and PSK modulation schemes. So to utilize these advantages or to overcome the limitations of the direct detection, there is a need or requirement for this coherent detection. So this is the fundamental concept of coherent detection as discussed previously. We will study this coherent detection with the help of a diagram. So in the coherent detection, what we have is, we have data, then we have carrier signal in the form of light that is generated using some optical source, for example LED. Then this carrier signal is modulated with the data signal. Okay, that is, characteristics of the carrier signal are modified according to message signal. So one characteristics that earlier we can modify was, for example, intensity. It is called as intensity modulation, or can be simply termed as ASK or OOK. But as discussed in the previous slides, in the coherent detection, along with the ASK, we can also use FSK and PSK, because at high data rates, the concept of this only the intensity modulation cannot be relied or cannot be depended on. So we also take the concept of into consideration is frequency as well as phase. So for the frequency and phase, we can also use the PSK modulation as well as FSK modulation. So on the transmitter side, we have a carrier signal in the form of light, then we have a message signal, data signal, that can be modulated either using ASK or PSK or FSK. Then the transmitted signal is passed through the optical fiber, which is acting as a channel. Okay. So as discussed, here we have the received signal, then we have a local oscillator generated signal W2, then these two are passed through a coupler or mixture, then is incidented over the combined signal is incidented over the photodiode or photodetector, and here only the intermediate frequency signal is allowed to pass. Basically, whenever there are two signals, for example W1 and W2, what we can get is either plus minus. So we can get, if two signals are same, we can get 2 W1. If two signals are same, we can also get 2 W2. If not same, then we can have W1 plus W2, and if different, we can have W1 minus W2. Now all these three signals are beyond the bandwidth handling capability of the photodiode. That's why the signal corresponding to these signal is rejected, and only the W1 minus W2 is allowed, which is the intermediate frequency signal. So here we get is WIF. Then we have a front end amplifier as used in the case of optical receiver, and then we have the filtering and demodulation corresponding to the signal, and finally we have the data output. So the main concept is, on the receiver side, the received signal is not directly incidented over the photodiode. In fact, it is combined with a locally generated optical signal, and the combined signal is incidented over the photodiode, and only the intermediate frequency signal is allowed to pass through. So as discussed, the signal in the coherent detection has the magnitude as well as frequency component as well as the phase component. So by keeping any two parameters constant, another can be varied, so that particular modulation can be used. For example, in the ASK, amplitude is varied and remaining two, phase and frequency, remain the constant, whereas for the FSK modulation, the amplitude is constant and the phase is also constant. So in the coherent detection, we can use ASK, FSK or PSK. Any modulation scheme can be used. So this is a simple detection process, as we have already discussed. The received optical signal, then we have a locally generated signal. These two signals are combined together and incidented over the photodiode or photodetector. And after detector, what we get is only the intermediate frequency to allow the signal. Then finally we have the electrical stream. So this is the mathematical. We can have a source signal ES equal to AS cos of omega st plus phi st. So this is one signal. This is the signal generated by the local oscillator signal, and as in the coherent detection, the source signal and the local oscillator signals are mixed together and incidented over the photodiode. So this is these two signals are mixed together, and the intensity of the coherent signal, this is the intensity corresponding to coherent detection signal. So the intensity is given by the square of the electric field signal, and electric field signal is obtained by the combination or mixing of the source signal with the locally oscillator signal. So the source signal plus local oscillator signal and square of this field, we get the intensity. So the intensity is given by this equation, and we know that power in the optical signal is directly proportional to intensity. So this equation can also be converted into the corresponding power equation. So this is what we are getting is power equation corresponding to the coherent detection, and we ensure that this power of local oscillator is much greater than the PS. This is to ensure the high sensitivity or better sensitivity response. Now next is, this coherent detection can be of two types. One is homodyne and another is heterodyne. Okay, as we know that homo means same and hetero means different. Through the coherent detection, what signal we are getting is intermediate frequency signal WIF given by WS minus WLO. Now if both of these two signals are same, that is WS equal to WLO, both the signals are same in terms of frequency or same in terms of characteristics, then what we have is, we will have is WIF equal to 0. This is the case for homodyne detection. That is, the signal that we are getting from the source or that we are getting from the additionally applied local source are same. So WIF equal to 0 is the case for homodyne detection. Whereas hetero means different. So in this case what we will have is WS is not equal to WLO. That's why intermediate frequency will have is non-zero. So this is the heterodyne case. In the case of homodyne, we have to match the characteristics of the two. So there will be a requirement of tuning, or we have to use some kind of PLL circuit, phase lock loop, and moreover this tuning and mixing is not easy. We are using additional PLL, so the cost is also high. But as the characteristics of the two signal is properly matched, so the performance in this case is better. Performance in the case of homodyne is better. Whereas if we compare this heterodyne detection with the homodyne detection, there is no requirement of matching of the two signals. So when there is no requirement of matching, so it is very simple and easy to implement. Plus, when there is no requirement of matching, so there is no requirement of tuning circuit or PLL circuit. So this is also advantage. Moreover, cost is reduced, but performance in this case will be slightly down as compared to the homodyne detection. So this is the case of homodyne and heterodyne detection. And if we put in this case of homodyne, what is the condition for homodyne is WIF equal to 0. So this factor WS minus WLO becomes 0. Okay, and this cos 0 is 1. So in the case of homodyne detection, this frequency terms gets eliminated, and if frequency terms get eliminated, we can only vary either the amplitude or the phase. So in the case of homodyne detection, we will be able to apply only either ASK or PSK. FSK cannot be applied. So this is the limitation of homodyne detection. And if we compare with this heterodyne detection, this heterodyne detection case is WIF is non-zero. Non-zero means frequency term is available, and if frequency term is also available, we can also vary that term. So in the case of heterodyne detection, we will be able to get ASK, FSK as well as PSK modulation scheme. So any of the modulation schemes can be applied over the coherent detection when we apply the heterodyne detection. We can see a number of advantages are there in terms of heterodyne detection, but overall performance is better in the homodyne detection. So this is mathematically that I have already explained homodyne detection. Homodyne detection is, we have intermediate frequency equal to 0, and when we put intermediate frequency equal to 0, there is no frequency term, only the amplitude term is there and only the phase term is there. So that's why we can apply either OOK, that is ASK, or PSK only. So in the homodyne detection, the FSK cannot be applied, but we get advantage of better performance, but there is disadvantage. There is requirement of matching, tuning, additional PLL circuit or tuning circuit may be required. That may also cause some increase in the cost of the system. So these are the advantages and disadvantages for the homodyne detection. Similar way, we can study for the heterodyne detection. In the heterodyne detection, there is condition that there is no requirement of matching. So the intermediate frequency is non-zero for the case of heterodyne detection. And if WIF is non-zero, then there is no change in the power equation and all the factors are available, and we can apply ASK, FSK as well as PSK modulation schemes with the heterodyne detection. And we will study the advantages and limitation that we have already studied. In the case of heterodyne detection, there is no requirement of matching. So IF is non-zero. So there is no requirement of tuning or PLL. So cost will be less, but performance will also be slightly degraded as compared to the homodyne detection. So that's all for this lecture. Thank you everyone. Jai Hind. This is the reference book.